Welcome back, students. In the last lecture, we considered the VSEPR model for making polyatomic molecules and attempted to reconcile this model with orbital theory, atomic orbital theory, by using hybridization. We saw that by combining s and p orbitals in different ways, we could construct hybrid orbitals that point in the directions we expect for sp, sp2, and sp3 hybridized carbons. And we even did this for non-equivalent ligands. However, we still have this inherent problem with this VSEPR model, that is, VSEPR predicts that electrons are localized in bonds rather than spread out over the entire molecule as MO theory would predict. And today we're finally going to have a chance to compare these localized, the valence bond hybridization model, and the delocalized model being MO theory. So the learning goals for today are to compare and contrast our valence bond theory and our molecular orbital theory, so our localized bonding model and our delocalized bonding model. And we're going to see that you can actually use MO theory to predict the bond angles. Remember, that was one of the shortcomings of our hybridization theory, is that we couldn't explain why water had a 104.5 degree bond angle. So hybridization theory, valence bond theory, has some great successes, and it also has some shortcomings. So its success is that it allows us to connect Lewis structures in the VSEPR model to quantum mechanics. So it explains why we can have different types of geometries. So for example, sp3 or sp2, even sp hybridized carbons. It explains why we can have these despite p orbitals pointing in the three cardinal directions and not at 120 degree bond angles or what have you. So this helps us to understand why the bond angles are the way they are. We're hybridizing s and p orbitals. And it works very well to predict the bond strength based on the character of s orbitals. So the more s character an orbital has, the stronger the bond is going to be. However, there are some very legitimate shortcomings as well. So the most prominent one is that we can't actually construct our hybrid orbitals without knowing the bond angle. We can't predict the bond angle using hybridization theory. We have to know it from either observations or something else. And as we saw with water, this is pretty challenging for molecules that don't all have the same ligand, so asymmetric molecules. And we still have this kind of weird hang-up that it implies, again, like we've been talking about, that the electron density is in between the bond rather than spread out over the whole molecule, as we would expect from MO theory. So what we have is this contrasting models. We have our valence bond models in which we have electrons localized in bonds. And so if we were to construct orbitals for these, we would say that these bonding orbitals from our valence bond theory are the orbital from the hydrogen atom here, and then some contribution from the s and p orbitals of beryllium. Again, this is a beryllium dioxide here, or dihydride. And then for the other orbital, we would have some contribution from the other hydrogen atom, right? The electron from the other hydrogen atom, and then some mix of the s and p orbitals for beryllium again. And this would describe our bonding. However, MO theory doesn't do that. MO theory works off of symmetry. So MO theory predicts a lower energy orbital that has no nodes, a higher energy orbital with one node, but the orbital you can see is spread out over the whole molecule. So the orbitals for this are not simply based on s and p orbitals, right? But what this orbital is a mix of all the orbitals. So in this case, we have a molecular orbital based on the 1s orbitals for hydrogen A and B and the 2s orbital. And up here we have, again, the 1s orbital for hydrogen A and B and the 2pz orbital. So the difference here is that in the valence bond theory, our orbitals are coming strictly from one hydrogen and then both orbitals of beryllium, whereas in our MO, we're using both hydrogens and then only one of the orbitals of beryllium. And this is, of course, a simple approximation here. So how can we use both of these models, right? Have we been teaching you something that's not true? Is valence bond theory and Lewis theory not true? And of course, we should not jump on that bandwagon too fast, because this is very accurate in terms of predicting the shapes of molecules. And we've already seen earlier in the class that we have things like STM that predict or show experimentally the shapes of molecules that we predict using Lewis theory. So that doesn't quite seem to be the case. So we can use, technically, we can use MO theory in a quantitative way, and we can do this by solving the Schrodinger equation, which gives the ideal of orbitals and bond angles and so forth. And this is what a program like Gaussian would do for us. What we're going to do in this class is not try to directly evaluate the Schrodinger equation. That's going to be much too challenging for us since we're humans and not computers. But we're going to take a qualitative approach, but this will still allow us to kind of understand how MO theory works. So what we're going to be trying to do is exploring why MO theory would give us a bond angle. So how can we get that bond angle out of MO theory? And what we're going to do is compare two molecules. We're going to compare H2O, so we're going to compare water, to H2 beryllium, so beryllium dihydride like we just saw on the last slide, and see what we can say about their bond angles. So we're very comfortable saying that water is bent, and we don't really know what the shape of H2 Be should be. However, if we go back one slide where we have an H2 Be, we can see that, well, what this molecule would have, it would not satisfy Lewis's octet rule, but we would have 4 electrons, right? So beryllium has 2 valence electrons, each of the hydrogens have 1. And so you put those together, we would expect that we have a beryllium with 2 hydrogens on it. And if we have no lone pairs, we should have a linear molecule with a 180-degree bond angle. That's our naive expectation. And again, our hybridization theory can't tell us what we have, but maybe MO theory can shine some light on this. So what would the atomic orbitals or the molecular orbitals for this H2X molecule look like? And to understand this, we have to go into symmetry, and we'll get to symmetry again. We're not quite there. We'll get there later in the semester, but we can use symmetry arguments and say, again, we have to have similar energies and the same kind of symmetry to get a molecular orbital. So what this is going to look like is essentially comparing the orbitals for beryllium. So we have a 2s, 2pz, 2px, 2py orbital. And then we're going to say, well, what can we do with the hydrogen atom 1s orbitals? How can they fit in to have the same type of symmetry? And we're going to see the same sorts of thing that we have always seen when we're talking about molecular orbital theory. If we have an orbital with more overlap, that is going to mean lower energy. So more overlap means lower energy. Of course, it's assuming that it's the same sign. And then the more nodes we have, the higher the energy is. And so again, this is the same sorts of thing that we've always seen for molecular orbitals. So if we were to look at this, again, what we're just doing here is adding the hydrogen atom orbitals into our beryllium atom 2s, 2px, 2py, 2pz orbitals. And the x, y, and z are, again, the dimensions are chosen arbitrarily, but we use these, again, so we can talk to other people about that. So we've chosen these directions. So if we look down here at the bottom, we can have the 1a1 molecular orbital, which comes from the addition of the hydrogen atom 1s orbitals and the beryllium atom 2s orbital. And this is what will also be true for oxygen. So these are all for not just beryllium, but for oxygen as well, and any H2X, where X is any of those second row atoms. And we can see that this looks like all 3 guys, right? All 3 s orbitals at the same symmetry. They can all add together. Now we have this label here, 1a1. We'll go into this in more detail later. This label comes from group theory. It's a category of symmetry. And just for now, treat it as a label, but we'll see where it comes from in a few weeks here. If we move up to the next orbital, and so this is a 2p orbital, and we've chosen the x dimension here for our 2p orbital, we can see that we again have some kind of overlap. So this type of x orbital is going to point horizontally here for us. And we have some overlap since we have two different signs of the p orbital. We have two different signs of our hydrogen atom 1s orbitals, which we can get by adding or subtracting the orbital to the density here. And we can get some good overlap. So here we can see that we have the plus lobe of the p orbital pointed in the same direction as our h atom 1s orbital, and here the minus lobe pointed in the same direction. Another thing we could get is with the pz orbital, where z here is up and down, and we can see that we can have a plus orbital pointed down in the same dimension as or direction as our s orbitals from hydrogens, and those are also plus, so we can have some density here. And finally, highest in energy, we have the py orbital, which points in and out of the plane and can have no net overlap with the 1s orbitals in the plane. And so we can have molecular orbitals that come from all of these atomic orbitals. And if we want to look at what they would look like, again, we can just simply imagine adding up these densities in terms of space. So here, if we have all of these guys in the same dimension, we add them together. Here, our 1b2 would look kind of like a big p orbital. We have our 2a1 and our 1b1. And then this here would be a higher energy orbital. That would be the anti-bonding orbital. And it's anti-bonding because there's no density between the bonds. So all the rest of these orbitals have density between the bonds. That makes them bonding orbitals. Except for, of course, this case, we have this non-bonding orbital here that is not interacting. And if we wanted to, we could, of course, construct an MO diagram for this, and we could fill this out. So it would be very similar to before. Here we have three equivalent H atom 1s orbitals that each would merge together, or two equivalent, sorry, and they would merge together. We have 8 electrons. We can go ahead and fill up our orbital diagram here. So to try to understand bond angle, we're going to look at what would happen to especially the overlap of these orbitals as we change the bond angle. And so note here, what we're going to be doing is comparing this for water, which is shown here. Water has 8 valence electrons, so all 4 of these orbitals have been filled. And then for H2 beryllium, only the bottom 2 would be filled. Since beryllium only has 2 valence electrons, we'd only have a total of 4, and we'd only be filling these 2 orbitals. And that's enough to account for the differences in the bond angle. So let's go ahead and look into that. Now, what can we do? How can we explain these bond angles? We can look at what would happen to these as a function of bond angle. So you can imagine, again, remember, lower energy means more favorable, more overlap. So if we start down here with the 1s, or the 2s orbital, sorry, the 1a1 molecular orbital, what would happen as we change the bond angle? So each of these H atom 1s orbitals is going to interact with the 2s orbital from the molecule here, the atom. It doesn't matter what the bond angle is, right? The bond length isn't going to change, so their interaction is not going to change. However, the smaller the bond angle, the closer these two guys are to each other, and they can start to interact with each other. And so what that means is that if we increase the bond angle from a bent angle here to a linear angle, we end up increasing the energy slightly because we remove the way that these two H atom 1s orbitals interact with each other. Now consider the next one, the 1b2 that's coming from the 2px orbital. In this case, these two are not interacting with each other at low bond angles. They have opposite sign. However, as we increase the bond angle, we go from a bent molecule to a linear molecule. Now the overlap is going to be much better when we get perfectly linear. We're going to have direct overlap between the 2p orbital and the 1s orbital from each of the hydrogen atoms. So that is pretty good. Up here for these higher 2 ones, so the 1b1 orbital is non-bonding, and that's regardless of the bond angle. Bond angle doesn't matter. It's always going to be non-bonding. We can't possibly have overlap. And the 2a1 orbital goes from having overlap with a bent angle. So again, here we have net overlap between the plus lobe of this p orbital and these two 1s orbitals. As we increase the bond angle, we lose that, and we become non-bonding once we get to a 180-degree bond angle. So with this, we can begin to think about what molecules would do, what bond angles be. And our answer in chemistry, our default answer, which is a good answer, is that the things that we observe, the things that happen, have the lowest energy. So for water to have a 104.5 degree bond angle would imply that that has the lowest energy. And from this graph, that's certainly not obvious that it's 104.5 degrees. Quantum mechanical calculations can show us this, but we can understand what's going on. So in this case, what is the driving force between having a 104.5 degree bond angle? If we increase the bond angle, that's unfavorable for this s orbital here, and it's very unfavorable for this 2p orbital here, this 2a1 molecular orbital, right? We would increase both of these energies. However, we decrease the energy for this 1b2 orbital. So, you know, what do we do? Which one do we actually take? And it turns out that it's an optimization of all of these. So the real molecule finds the energy minimum by satisfying all four of these orbitals where its electrons are. Now, the 1b1 orbital doesn't contribute because it's at a constant energy no matter what the bond angle is. And it turns out for water that this bond angle ends up being at 104.5 degrees. That satisfies the minimum of all of these functions. Now, beryllium dihydride, BeH2, does not have electrons in the 2a1 orbital. So what it has to consider for its bond angle is simply the 1b1 and the 1b2 and the 1a1 orbital. And it can do that by having a 180 degree bond angle. This goes down as a function of degree. This goes up as a function of degree, but this goes down to a greater extent than this one goes up. So the minimum is at 180 degrees. And so our MO theory here, again, we've used it in a very qualitative way, but it's capable of explaining this phenomenon of why H2O and H2Be would have such different bond angles. They're both doing the same thing. They're minimizing energy. And we can see how that happens here by using MO theory. Lastly, here, we want to do what I've been promising that we'll do for a week or so, and that is to reconcile the localized and delocalized bonding models. And again, these models appear to be at odds with each other. So how can we have a model that has electrons delocalized over the whole molecule and then compare that to one where they're localized in bonds? They seem to be different. So what we're going to do, again, we're trying to reconcile these different orbitals here. And the way that we're going to do that is by building the wave function for these orbitals. Now, how do we do that? We start by saying, well, what are these wave functions? So we're going to start with a delocalized model. So we have our sigma G and our sigma U wave function. This is for a beryllium dihydride. We could, in theory, do this with any molecule. It gets more complicated the bigger the molecule is, the more electrons there are. So our sigma G orbital here is the sum of the H atoms. So we have some constant times the H atoms, and then we have base addition of the beryllium 2s orbital. We have another orbital that is another contribution from the H atom orbitals, and then the beryllium 2pz orbital. And we saw this before on one of the first slides for today. And this mathematical function describes either of these orbitals, right? We have an orbital here where we have all overlap between all the atoms, and then we have this node, so we have a higher energy orbital there. And this one is clearly coming from 2pz, this one's coming from 2s. How do we construct a wave function, right? Well, we've done this before for atoms, and we can do the same thing for molecules. We simply have to construct a Slater determinant. So what goes into the Slater determinant is 1 over 4 factorial, where 4 is the number of electrons. And then in the columns here, we have the lowest energy orbital spin up, the lowest energy orbital spin down, the next lowest energy spin up, the next lowest energy spin down. And in the rows go electron 1, 2, 3, and 4. And remember, we use these Slater determinants because if we were to swap any two rows or columns, the sign of our determinant would be negative, and that's in accord with our Pauli exclusion principle, our sixth quantum mechanical postulate that the wave function must be antisymmetric upon the change of any two electrons. Now, there's another property of Slater determinants that is helpful to us here. And that is that if we add one row or column multiplied by a constant to another row or column, we don't change the value of the determinant. And if you've taken linear algebra or done any sort of linear algebra, you'll remember this as things like making your matrix into a reduced row echelon form. You do this sort of stuff. But we can see this here, right? The determinant of our 2 by 2 matrix is A times D minus B times C. But what's the determinant of this more complicated matrix? Well, it's A times D plus A times gamma C, and then minus B times C minus A times gamma C. And so that A gamma C will cancel out and the determinant is the same. And so what this means for us is that we can add components of one row to another row without changing the determinant of the matrix. And if we don't change the determinant of the matrix, that's the wave function. So we can do things, we can manipulate these orbitals without actually changing the determinant of the matrix, without changing the wave function. And so that means that if we do these kind of manipulations where we add different rows and columns to each other without multiplied by a constant, we have not changed anything observable and we haven't actually changed the wave function. And so we'll do something that maybe seems strange, but we'll see what's happening here. Is we'll take our sigma g column and we'll add our sigma u orbital multiplied by some constant. In this case, it's C1 over C3. Now, why do we do that? And we'll go through this math. It'll be on the homework. And what we can see is that when we do this, right, what do we get? We end up getting an orbital that is now based on one hydrogen atom and the beryllium atoms 2s and 2pz orbital. In other words, we have obtained a localized bonding orbital. And we can do this again with our other orbital as well. And so in doing so, we have not changed anything about the wave function. And so what this shows us is that our functions here, our localized models and our delocalized models, both predict the same wave function. So they are indistinguishable. They give the same values here. And so this means that our models, despite inherently sounding very different, and once we think about it for more than a minute, are actually the same thing and predict the same answers. So this is specifically for H2BE. We can, in theory, do this for any molecule and come up with the same conclusions here. The one thing to note is that these localized orbitals that we obtain are not eigenfunctions of the total energy operator anymore, which means that it's more easy to use the delocalized MO theory models. And typically that's what we'll do going forward. It's more convenient when our orbitals are solutions to the Schrodinger equation. So we can compare this. We can do things that we talked about before, calculating the electrostatic potential. And we find that that agrees pretty well with this localized model. So for ammonia, there's a buildup of electron density where we'd expect the lone pair to be. Same is true for water, same is true for hydrogen fluoride. So we see this localization of charge despite not assuming that when we go in and make the orbitals. The last thing I'll show for today, and I showed this before to you, it's using a scanning tunneling microscopy to offer experimental comparisons. We've seen this figure before back when we talked about STM towards the beginning of class. And here we can see some accurate predictions of what the HOMOs and LUMOs would be. And again, what we see is shocking. We shockingly see that our predictions here, our quantum mechanical theory, agrees very, very well. You know, it's almost a perfect match with the experimental data, where the electrons are going to or coming from when exposed to scanning tunneling microscopy. So keep in mind here that these models are built up using both molecular orbital theory and valence bond theory to predict things like the bond lengths and so forth. And both of these models, again, they actually turn out to be reconcilable. They give the same wave functions, and these are in very good agreement with experimental measurements. So I'll finish here, and next time we'll talk a little bit more about more complicated polyatomic molecules, how we can construct these using computation. Again, we'll talk more about symmetry. We'll talk more about computation later. And then we'll delve into Huckel theory a little bit to describe the orbitals of conjugated molecules. So I look forward to talking about this with you guys in class.